Bismillah ar-Rahman ar-Rahim. We will discuss today diffusion and osmosis. It's not that bad subject. Really, the most difficult one was the natural exponential functions to try to explain. So you must choose the proper timing to understand such a subject. However, diffusion means that the molecules are crossing either an area or a layer. You see? And of course, gases in the lungs cross the gas-liquid barrier, as we know. Of course, this diffusion is correlated to the concentration gradient, and this is the diagram showing how does the gases pass to the blood, and so through the extracellular fluid, and then lastly through the cell. The first law we'll be discussing, law of diffusion, is the Fick's law. Fick's law. You can, as you see, two compartments. There is a membrane in separated two compartments. So we have molecules out, three parts of molecules upwards, and on the right side more than that. So the rate of diffusion of the right sided molecules definitely is more than the left one, and this is what we call about Fick's principle. You see. Of course, you must have slight modification whenever this molecule is transferred from, suppose, a gaseous state to a liquid state. At this point, we call the dissolving gas in the liquid tension. So if this gas is more dissolved in the liquid, there will be more concentration gradient. The diffusion rate will be much increased. Of course, this area is affected by its capacity. Whenever the capacity is large, definitely the diffusion rate will be much improved. You see, whenever I have a flow of gas, I want to discuss its diffusion, I must multiply the amount in its concentration to get the proper meaning of the diffusion of this amount of gas. Pulmonary diffusion capacity is the capability of the lung to transfer gases easily. You know that there are many diseases as asbestosis, sarcoidosis, lupus erythematosus. All these are diseases that affect the diffusion of gases, definitely. So we use what we call diffusion capacity testing. We're using trace amount of carbon monoxide around 1% to be breathed by the human being. Of course, you know the affinity of carbon monoxide for hemoglobin is much more than the oxygen, so it diffuses rapidly, combining with hemoglobin to the extent that there is not enough time in the capillary vasculature to denote this carbon monoxide. In other words, the flow of the pulmonary circulation is not much affected by this diffusion. You see. I'm sorry because I'm using also the laser pen and making mistakes. So this is the first test of the capability of the lungs. Of course, if you have any pneumonectomy, it will be much affected, of course, by this. Of course, if you have edema, of course, it will affect the diffusion. Practical aspects of diffusion. We have, as we know, that isoflurane is soluble in rubber, and it can be retained in the anesthetic tubing system, and it could be a source of delayed recovery and contaminating the theater, and it could be initiate what we call malignant hyperpyrexia. Also, we can remember that the compression sickness, where the sea divers go downwards to the sea, and then the pressure of nitrogen is increasing, coming out in bubbles, obstruction knees and pulmonary circulation and so on. So this is based on the diffusion, also on the fixed principle. Of course, someone, as we know that the dissolving of nitric oxide more than nitrogen, so nitric oxide diffuses through capacities where nitrogen is present, and as there is a pressure gradient between nitric oxide and from what's inside the body and what's outside, it goes speedily outwards, causing bubbling, as we said before. And this also denotes how nitric oxide diffuses into cavities, increasing the cavity's size. Of course, if you have a solitary cyst and so forth, or in the middle ear surgery, it will increase the tension. All this is based on the diffusion or the rate of diffusion. Now, the second item in the factors affecting diffusion is the molecular weight. We have an example. If we have a broken a pipe releasing hydrogen gas, and we have a broken bottle of ether. Of course, hydrogen is lighter than ether, so it ascends upwards easily. On the other hand, the molecules of ether are spread over the floor, creating what we call a blue flame downwards. You see, this is based on the molecular size. So Grams states that the rate of diffusion is proportional or inversely proportional to the square root of the molecular weight. So that carbon dioxide will diffuse less than oxygen, because the molecular weight is 44, but the oxygen is 32. But on the other hand, this is not much correct through complex biological membrane where carbon dioxide is more dissolved in water, so that it diffuses more, though its molecular weight is much smaller. You see that the other point, that the diffusion of liquids is different than the diffusion of gases. As you can see, we are injecting piperacin to induce local anesthesia. So if you are aware of the nerve to be concerned, it would take a long time for the local anesthetic to diffuse to reach the target. So you must be precise while doing blocking of the nerves, based on the diffusion, of course, of the diffusion of liquid is much difficult than that of gases. Osmosis, by another way, of course, diffusion is governed by the two laws, as we mentioned. Also, the passage of gases through liquids are governed by osmotic pressure and osmosis. This is another factor we're going to talk about. Osmosis is the character of molecules in the human being. As you can see, this is a big compartment divided into two by a semi-permeable membrane. It is a semi-permeable membrane. You see, so on the left side we put a solvent, and on the right side we put a solution. Solution means a solid and a solvent. You see, so according to fixed principle, this molecules of the solvent go from the left side to the right side according to fixed law. But the solid present in the solution will hinder or counteract the effect of this diffusion. So the diffusion is limited. At equilibrium, we will find a height. This height, of course, of the diffusion of the solvent to the solid. This height, we call it the osmotic pressure. The capability of the solids in the solution to hinder or to counteract the effect of passage of the solvent to the solution. Of course, on the other hand, if we, in this compartment, as we mentioned before, we created a scenario. This scenario is present that we have a temperature of 0, and we put in the right side 1 mole of a substance, and this capacity of this compartment is 22.4. As we mentioned before, of course, 1 mole of any gas occupies 22.4 at standard temperature and pressure. So we are creating a scenario. At that scenario, the pressure yield will be 1 atmosphere. 1 atmosphere. So that any solid you want to know its osmotic pressure, whenever you put it in this compartment, it will yield an osmotic pressure which is due to the power of the molecules to create an osmotic pressure. And you can also give a hint about the number of moles of this solid present in this right compartment. We have now the Ringer lactate solution. You can see that the components of all the components, sodium, potassium, calcium, and lactate. Of course, lactate must be in an ionized form so that it can act as a molecule given an osmotic pressure. We find that components of it is in millimole, millimole, millimole. Of course, we can make a molar solution by putting 1 mole of solid in 1 liter of liquid, and each milliliter will contain 1 millimole. So this is the components of the Ringer lactate. These components, of course, induces an osmotic pressure according to the molarities or the molalities present. Molarity and molality. Molality means that the osmoles are dissolved in 1 kilo of water or solvent. On the other hand, the molarity means the dissolving of these molecules in 1 liter, in 1 volume. I'm sorry, 1 volume. See, so what is the difference? That temperature is not much affected by the molality whenever you dissolve these molecules in a kilogram of a solvent. So molarity and molality, or osmolality and osmolarity, are similar. The molality gives osmolarity. You see, the components of this particles in the Ringer lactate gives an osmotic pressure of around notice not around 287 and 78. You see. Of course, the osmotic pressure creates a pressure, you see. So this is the capillary loop, as we can see. Sometimes the book gives me the figure before the announcing of it, you see. So sometimes the explanation becomes difficult sometimes. So this is the capillary loop. You have a venous side and arterial side. The pressure, the hydrostatic pressure of the arteria is 7.5 kilopascal. Of course, you can shift it to millimeter mercury. And on the other side, the venous pressure is 0 kilopascal. The oncotic pressure, we will notice later on, is the pressure yielded by the albumin or the protoplasma protein is 3.5, half of the arterial. See what happens at this loop. Of course, the pressure, hydrostatic pressure of the capillary blood pressure is capable to transfer the fluids out of the blood vessels to nourish the tissues. And then after the tissues being nourished, they are being taken back, of course, against a concentration gradient pressure, 0 and 3.5 accordingly. So if you have a very low plasma protein, it will affect this drainage, and if it will lead to what we call edema. So most of the fluids, the blood pressure, osmotic pressure is around 300 milliosmol per liter. It's mainly 99% of this pressure. This pressure is due to sodium chloride and bicarbonate. 99 of the osmolarity of the plasma. The 1 milliosmol of the plasma protein of mainly is for albumin, you see. So the osmotic pressure correlated to plasma protein, which is mainly due to albumin, is called oncotic pressure, you see. Of course, this osmolarity of the blood, whenever I put a fluid similar to it or nearby, I call it that I'm admitting an isotonic solution. The red cell fragility test is a test to identify hemolytic anemias. Of course, when I induce a hypotonic solution in a normal human being, this hypotonic solution makes the cells enlarge. Of course, if you have a bad wall integrity of this cells, definitely this cells will break down easily. And this is the basis of the red cell fragility test to test the patients with hemolytic anemia. The measurement of the oncotic pressure of the plasma is oncotic pressure by an oncotometer is based on the compartment scenario we mentioned before, that we have two compartments. On the left one we put a solvent, and on the right one we put suppose plasma instead of saline, and that we will notice how much this plasma can hinder the passage or to induce a counter effect on the passage of the solvent from the left side to right side. It will create a pressure. This pressure, of course, maybe I forgot to tell you, it can be yield through a height, or it can be if the compartment is closed from upwards, which will be shown later on this diagram. It will be read by a dial. You see. Osmolarity and renal function. Of course, as you know that the pulmonary membrane transfers the components of the blood through the kidney to filter, to remove much of the water. So as we know, as we said before, the amount of osmoles present in the blood is around 300 million osmol per liter. And whenever absorption occurs to the water in the renal tubules, of course, the end results yields urine osmolarity of 1,000, 4 times. You see, so if there is a defect between, or there is a much change, of course, if we give diuresis, this osmolarity will be affected. Renal function will be affected. So this is a figure between the osmolarity of the blood and that of the urine, which can give us an idea about the situation of the kidney. See, so this is the paragraph showing the osmolality and osmolarity. As we said, osmolality, this is much by scientific researcher used, is the amount present in 1 kilogram of the water of solvent. On the other hand, the osmolarity is on the volume. And as we said before, the osmolality is not affected much by temperature. Measurement of osmolarity is based on the characters of molecules. You see, this is called the colligative properties of molecules. The first test to measure osmolarity is based by the capability of the molecules to decrease the freezing point. Imagine that whenever we go to Europe, they always throw saline on the snow, so that it will the freezing point will be decreased by 1.86 Celsius. Imagine that. Yeah, this is why it could be a small question whenever I want to give a question about this subject. Why do we throw saline over snow in Europe? What is the test? This test is called the capability of the molecules to decrease the freezing point of the substance. Now we have a container, a glass cup, something like a cup. We put 2 milliliters of urine. We want to know the number of milliosmol present, and then we have a vibrating stirrer. Stirrer means we stir on, and then we put it in a refrigerator bath. This refrigerator bath can create what we call super cooling. It cools beyond the freezing point. You see, less than the freezing point, and then we begin to increase the temperature till freezing occurs. You'll see the the character of freezing occurring. At this point, you can utilize the temperature, and we have above the meter can transfer this temperature into millimoles directly. You see. The second character of molecules is decreasing the saturated vapor pressure of a solvent. As we see the two compartments, the semi-permeable membrane and the solvent going to the right side, hindered by the presence of solid. Whenever you can see on the left side, the molecules are coming out from the liquid, inducing a vapor, and it will create, of course, a vapor pressure. On the other hand, on the right side, we'll find that this solid present on the right side will hinder the evaporation of the solvent present. So this is called Rhodes phenomenon. This Rhodes phenomenon is based, and accordingly we use it to measure the osmolarity. You see, as long as the vapor pressure is decreased, the boiling point is increased. All these characters of the molecules are utilized to estimate its number of moles of any substance in any given solution. Azeotrope, as we say, that solvent is being dissolved in the liquid. You can combine two liquids dissolved in each other at a rate according to. We have ether and halocene. We used to use it before to evaporate both of them at a certain vapor pressure. This is metered, of course, because we know the molecular weight of both, we know the volume of both, and so on, so that we can create a vapor pressure, but by a special percenting, which can be utilized to anesthetize the patient. This combination, of course, one particle of ether and two particles of halocene can yield what we call azeotrope. This azeotrope also can be used whenever I want to dilute alcohol to be instead of 100% to be 96% by dissolving it in water. And it's very difficult, of course, to increase the concentration of alcohol beyond this point. I hope I did a good job. I hope so. I'll improve myself later on. Wassalamu alaikum wa rahmatullah wa barakatuh.